Vincent Coulihan.
Hey, thank you very much. Thank you. Thank you. It really has been a great day here for NEAF 2019. From us in Rockland Astronomy, we really want to send a real big shout out to all you for being here and supporting this, and we think and hope that you really are enjoying yourself. Before I get going with the introduction, though, I want to take a moment to thank the people that are working behind the scenes here, our AV crew, the people who are making this production happen for us, and it can happen so professionally. So we'll give them a big round of applause, please. Thank you. Our next speaker is a chief scientist from NASA. He focuses on NASA's strategic space science missions. Prior to that, he was director of Planetary Science, working on projects from Mercury through Pluto. Please, he has a Ph.D. in space physics from the University of Iowa. I definitely wanted to mention that. That's kind of important. Please welcome to NEAF 2019, Dr. Jim Green. Thank you. Thanks.
Well, it's really wonderful to be here. And of course, this is the anniversary of Apollo 11. 50 years ago, July 16th, they launched. And we're going to talk about that mission, and in particular, several of the Apollos and what we learned from them, and then how we built on that to understand the origin and evolution of the Earth. And then we're going to take a look into the future and look at what's next for the moon. So indeed, this is a tremendously exciting time for us. Now, to start out, in the 60s, when President Kennedy said, we're going to the moon by the end of this decade, not because it is easy, but because it is hard. And we started a program to be able to understand everything we could before we landed on the moon with humans. These would be called Precursor missions. Because after all, NASA doesn't do Star Trek. It's not go where no human has gone before. We really want to understand everything about it. And that's where this set of missions comes from. These are the IMP missions, the Interplanetary Monitoring Platform missions. I personally, when I was at the University of Iowa, worked on IMP6 and IMP8 data. But they were revolutionary for understanding that something was happening in that void that looks black from our eyes. But in reality, it's full of plasma. It's full of streaming particles. It's full of electromagnetic waves that we can't see. And indeed, we didn't even know early on the extent of the magnetic field that is generated interior to the Earth, how far out into space it goes. And so as you can see, these missions blanketed the area between the Earth and the moon, with one even orbiting the moon, to really understand what that environment is like. And the solar wind shapes the magnetosphere. And we discovered the magnetopause and the bow shock and the magnetotail. And in fact, a significant part of the time, the moon actually stays in the tail of the magnetosphere and is protected in many ways against the solar wind. Now, in addition to the plasma measurements and the magnetic field measurements that we made, and this included a little bit of the Van Allen radiation belts, which were discovered in 1959 by James Van Allen and Explorer 1, we launched 21 precursor missions straight to the moon. Now, we did it in a very methodical way. You fly by, you orbit, you land, you rove, and you return samples. And here is a list of all the missions from all the nations that have gone to the moon in these four or five categories. Now, some of these were very successful. Some of these were really not very successful. We tried actually to hit the moon and missed it. How could you do that, right? But these were the things that we had to learn as we went along the way. Now, also on this list, particularly the orbiters, there's several here like LADEE and the Lunar Reconnaissance Orbiter that we've launched since the Apollos that have really made enormous progress in understanding much more of the moon that's going to help us into the future. Here is really where my story starts with our three heroes, Okay, Buzz Aldrin, Neil Armstrong, and Mike Collins. They were going to go on a huge Saturn V. The SLS that we're building today is 10% more capable than the Saturn V. Now, I never saw Saturn V launch, but I heard from those that have that when you're at that 3-mile distance away and the Saturn V takes off, the ground shakes. So if you have an opportunity to go to an SLS launch, I think that would be pretty cool. Now, of course, once they launched, they had to, in orbit, rearrange both the lunar module and the command service module, the capsule that they were all in, into this configuration, and then took this to the moon, got into orbit around the moon, and then Buzz Aldrin and Neil Armstrong got into the lunar limb. This would be the Eagle, called the Eagle, and then descended to the surface. Now, there's quite a story about Neil avoiding some things. He took over control, not going down to where they were supposed to go down, and he told Buzz, read off how much fuel I have left. So Buzz is doing the countdown, and Neil just cruises over this debris field, which actually is a cratered area, and then moves beyond and lands with just, vapors in the tank. Pretty spectacular. Now, first thing he does is he starts down the ladder after he gets ready, and he's going back and forth with Houston, letting them know what's happening, what he's seeing. And the first thing he talks about is how the lunar limb is situated in the regolith. Now, we had a lot of Precursor missions. Many scientists, planetary scientists at that time, felt that the lunar regolith may be so high in some areas that you could actually sink into it. It would come up to your, high up on your legs and maybe even your chest height. They just, really didn't know. Now, when we landed, the surveyors, they seemed to be in fine shape. And so first thing Neil wanted to do was look at the legs and see the impression of that leg in the regolith, and he talks about that it hasn't gone down deep. The regolith may only be a few centimeters thick. Then he comes down the ladder, of course, and says, one small step for man, one giant leap for mankind, steps off the ladder, and now he's on the moon. He then sets up a camera, and Buzz can't wait to get out of the capsule, and Buzz is hurrying out, and Neil helps him, talks to him as he comes off the ladder and gets down on the moon. And then they go to work. So for the next several hours, they deploy some instruments. Two of the most important instruments are a seismic instrument. That's the one that's shown here. And right behind it, it's sort of hidden, is a second instrument, which is it's about a 1.5 by 1.5 feet of reflecting mirrors. Okay, and put that down on the moon. And then, of course, they return to the capsule. Those two experiments are tremendously important. Seismic-wise, we wanted to know if the moon shakes. Is there moonquakes? And the answer to that is yes. And unfortunately, the Apollo seismometers didn't take into account how complex the seismic environment of the moon is. The crust rings. And so consequently, we don't know a lot about the interior of the moon, but that I think will change into the future. So here's a little overview of a modern look at the landing site for all those that may think that we didn't really go to the moon. Well, this was really a pretty spectacular event. And of course, what happens next is a whole series of other lunar landing missions. Apollo 12, Apollo 13, the famous mission that didn't actually make it to the surface, but challenged NASA in many unique ways. It really got us to be thinking in a new paradigm for which every mission we started to approach from then on, we had to go through what-if scenarios, extensive what-if scenarios, to be able to develop contingency plans. Rather than do those, on the fly, we really wanted to have the background and the rehearsal, and that tells us also about potentially extra equipment we may need on board. After 13, of course, 14, 15, 16, and 17. And even though from Apollo 11, they didn't walk any further than the size of this theater, Apollo 17 went 4 or 5 miles away and really scouted out the area. Now, each of the Apollo missions brought back lunar material. They brought back regolith. They did some cores, brought that material back. They brought back about 850 pounds of lunar material. And that's the gold that we've been mining ever since. We've set a significant amount of that aside, about 60%, that we haven't really looked at. And we've interrogated in many ways the rest of the material to scientists throughout the world that have developed the capability to really analyze and tease apart what's in these samples. Well, since the Apollos, we've had a number of missions. And I'm going to show you data from several of those. This is data of the moon, both on the near side, but the far side. Okay, there's no such thing as the dark side, okay? You all should know that. You're astronomers. That's good. Great. Don't have to explain that. So the near side, when you look at the near side and the far side, from the Lunar Reconnaissance Orbiter, which is still orbiting today, is very different. This is really important for us to understand. And we see these Mari, and the Mari are these dark areas. These are from impacts that have occurred, excavating a significant chunk of the crust, and then lunar magma, molten rock, pours into those areas and covers them, filling them in, creating that basaltic look, that Mari look about the moon. On the far side, there's hardly any Mari. There are highlands, many craters, and in fact, when we tease out the altitude structure, also measured by LRO, and color it, this is what we see. So if you imagine the reds and the whites being the highlands, and the blues and purples more of the lowland, you see the highest peaks are on the far side, and the lowest valleys are on the far side. And in fact, this one particular area on the far side, we call the South Pole Aitken Basin, is a huge impact region. So the moon ran block to the Earth that day, and it blew away a significant amount of the crust in this impact. And so what's laying there may be mantle material, upper mantle material, but certainly lower crust material. Now this is important. We can't get to the mantle of our own planet, and yet how pressure squeezes and changes the mineralogy of the rocks that are available to us in the lower crust and upper mantle are sitting on the far side of the moon for us to get to. Now in many ways, we know more about the surface of Venus than we do the far side of the moon, because we haven't landed there. And we plan on landing there. We want to go to that far side. What's inhibiting us, of course, is the ability to communicate back and forth. Also, the altitude differences between those white areas on the peaks and in the South Pole Aitken Basin is about 14.5 kilometers, okay? So that distance is greater than the top of Mount Everest measured to the bottom of the Marianas Trench. which is only about 11 kilometers. Okay, so the height difference that we see on the moon is spectacular on the far side. We also, with the Grail mission, and these are two spacecraft that followed each other in orbit, and as the gravity of the moon would pull on one first and then the second one, we'd measure the distance between the two, and that would tell us about the mass concentrations that are in the moon at various locations. And we put this data together, and we can get the thickness of the crust. And so this is now colored in thickness of the crust. And you can see the thick crust on the far side. In fact, it's typically 30 kilometers thicker on the far side than it is on the near side. Now, any knowledge that we can get like that will help us in trying to figure out how the moon came about. So we have to consider crustal thickness in its evolution. So let's talk about that. When we brought back those rocks and we started to age date them, we were surprised. The surprise is that those rocks from the moon are older than the rocks here on Earth. We can't find a rock on Earth more than about 3.8 billion years. And yet, material from the moon was giving us 4.5, almost 4.6 billion years. So lunar rocks were already telling us these are really pristine. In other words, soon after the moon was created, and whatever atmosphere it may have had at the time has dissipated, it is recording the bombardment history from 4.6 billion years when it was created to today. And so we have to think about how those things fit into its evolution. So 4.6 billion years ago, we believe a supernova not far away began after it exploded a process as the waves filtered through the large cloud that we are from, came from, and that started a series of condensations. Several hundred stars were probably created in that event. The sun was being created, and planets started forming. So as the material was moving from a cloud into a disk, conserving angular momentum, and the sun was accreting most of that material, planets began to arise. So now we want to talk about what those planets did over time. They became big enough and hot enough that their cores, as they melted all the material, contain the heavier elements. This would be the iron, this would be the magnesium, all the heavier elements would sink to the center. And then you'd have lighter materials, which would be in the mantle, and then even lighter materials, the silicate rocks on the crust. So from our analysis of the lunar rocks and the ages, the theory that fits the best is an impact theory of two bodies, two Earth-like bodies that were created in our orbit. One about the size of Mars, and the other one on the order of the size of the Earth today. Now we call that other body Theia. So there's an impact that occurs, we believe, between Theia and the Earth as they are accreting in pretty much the same orbit. Now today, our computer capability is so great that we can actually model this. And so, we go from that illustration into the computer model where you can break up each and every bit and then watch it occur, putting into the computer all the physics and dynamics of an impact. And so I'm going to show a movie of this impact. This is the top theory that we have going from Theia and a Earth-like planet into the Earth-Moon system. So there's the initial impact. We believe it was a glancing blow. The core of that planet, you can see it in the lower right, comes back into the Earth. So the core of Theia comes back into Earth. And then that is combined with our core. and material starts then to accrete to Earth. Now there's a certain region of control that the Earth has of material that falls into it. It's called the Roche limit, and outside the Roche limit, other larger bodies can form. Now we're looking at a region for which we're all inside the Roche limit, but outside the Roche limit, now larger bodies can form and stay stable. And so what happens now is the moon begins to accrete away from the Earth outside this Roche limit. All the material inside the Roche limit falls onto the Earth. Now the Roche limit, when you think about it, is really as a body is accreting inside the Roche limit, gravitational pull is greater on one side than the other, and so it keeps the pieces from really accreting into any substantial mass. And of course that eventually comes into the Earth. And so we end up in this computer model with, after only probably several weeks to maybe several months after this collision occurred, to this situation, an Earth and a moon just outside the Roche limit, which is 3 Earth radii away. Now, what on earth makes us think that this is realistic? Okay, right? And it comes back to Apollo 11. For the last 50 years, we've been hitting with lasers that retro-reflector, and we find the moon is moving away from the Earth 1.5 inches a year. All right? So once we know the age of the Earth, which we also obtained from Apollo rocks, 4.6 billion years, and move the moon inward, knowing that it has to exist outside the Roche limit, it has to start this way. Now what's really exciting is that one day on Earth was 5 hours long, okay? And the moon is so close, it's tidally locked. The Earth is going to hang on to that one surface that constantly points to it, okay? And so as other impacts occur, magma will also be attracted to that area. So we believe, based on the thin crust on the near side and the tidal lock so close to the Earth that occurred right after it's made, that that magma then is going to fill in these impact regions only on the near side. So, sounds like that fits. But here's what happens over time. So the moon forms and it begins to move away from the Earth. And like the ballerina that spins, once she puts her arms out, she slows down. And so we go from 5 hours on one day, 24 hours today, and the moon from 3 Earth radii away to 60 Earth radii away. Now, if you were standing on the Earth, well, I wouldn't have recommended it 4.6 billion years ago, and looked at the moon, it would be 16 times larger at that location outside the Roche limit than it is today. It would have been a spectacular sight. So that begins to fit. Well, what about the far side? What about this extra thick crust? And I mean, it's 30 kilometers thicker. That's a lot of material. We have 2 basic theories for that, okay? And the 2 basic theories are, 1, yes, we believe the moon formed outside the Roche limit, but perhaps there were 2 objects. Another object perhaps smaller than the moon, and that object would eventually impact the moon. And computer modeling seems to indicate that much of that material, depending on its size and some parameters of the impact, would indeed have left the far side of the moon with a thicker crust. But that's only one of 2 theories. Another theory is, during this time period, the Earth is enormously hot. This is called the Hadean period. It's hotter than hell, as they say. And so in that period, the heat from the Earth is literally baking that near side of the moon to the point where material must be blowing off. And so this is a time when the moon is outgassing, it has its own atmosphere, it's boiling, the volatiles, which would include water, are coming out, leaching out of the surface, and they are moving. And so one of the other theories is indeed that material ends up falling on the far side of the moon, creating that thicker crust. So from Apollo 11, getting the distances right, from our age of the rocks, all that fits well. And indeed, now we can begin to look at the moon as that time history of impacts. So for every one impact on the moon, there are 20 on Earth, okay? So when we look at the moon and we see so many impacts, we must immediately recognize how hard the Earth must have been bombarded over those 4.6 billion years. Now, that bombardment history is hardly observed. You know, we're finding various craters all over the place. Eugene Shoemaker did an enormous amount of work at Barringer Crater and convinced planetary scientists in the 60s that the craters on the moon were from impacts, not volcanic. A lot of scientists believe they were volcanic in origin. They're not. They're impacts. There's only a few volcanic areas that may be slightly active or active at least in the recent past within the last 10 or 20,000 years. But by looking at the craters now on the moon, we can understand the history of the solar system, the bombardment history of the inner solar system as our planets moved around the sun, sweeping up the leftover crumbs. And so that's very important. We can see that the cratering rate away from the Mare is different than that in the Mare, but those are different epochs. And so that cratering history is so important for us. If we can date the Mare, which we have, then we know how many craters have been hitting the inner part of the solar system, at what frequency and at what size, such that we then can age date Mars. And we can age date the moons of Jupiter and on into the solar system. So this is an incredibly important set of observations. So we also know the mineralogy of the surface. Now, the mineralogy of the surface, even though when we look at the moon in visible light, it's grayish and dark, but if you had infrared light that you could see with your eyes, this is what the moon would look like. It's full of all different kinds of material that have come from the impacts. This is just a spectacular array of material. And of course, we've only been to the Apollo sites. Those are the material that we've retrieved. They're limited in latitude. And so we have all kinds of places that we need to go on the moon. These are where material the moon has acquired over time that was created at a different location and perhaps a different time and brought to the Earth. So when we begin this age dating process, we can begin to look at the impact regions and we can age date them. And one of the more spectacular things popped out. Some of them are very young. 3.6 billion years ago, some really big impacts occurred on the moon. So it's almost like, hey, the moon was created, a lot of impacts occurred, it should have died down, and then all of a sudden, 3.6 billion years or 3.8 billion years ago, all kinds of heck broke loose in the solar system, bombarding everything in the inner solar system. This now is another piece of information that tells us how the solar system was put together. In the early 2000s, a group of modelers, their supercomputing was getting so good we could model the accretions and creation of the entire solar system bodies, came to Nice, France. And at Nice, France, they had a wonderful conference, and they all got up to talk about how their computer model was creating the solar system. And of course, they all failed. They couldn't create it. They let their codes run for 5 billion years, and they couldn't create Uranus and Neptune. And yet we know all the planets were created within at least no longer than 10 million years. 10 million years from 4.6 billion years ago. So the solar system came together rapidly. So they went out to dinner. They all talked about what physics they're missing in their models, and they drank more wine. And one of them said, well, heck, what did we learn? Well, we learned we can create the stuff faster if it's closer to the sun. So let's forget about our solar system, and let's move the planets, the seeds of the planets that we start with our models, and see if we can create all the planets within a 10 million year period. Okay? This is called the NEAF model, okay, because it was done in Nice, France. They went and did this. Now I'm going to show you some of the simulations that result from that. Now what you're seeing is you're looking down on that right-handed panel from above, and you're seeing the circles. Those are the orbits of Jupiter, Saturn, Uranus, and Neptune. And the green area are the leftover bits of material that are being created, both rocky, but also icy materials that are accreted, that remain after the initial creation of the planets. Now, because they had the opportunity to let their codes run, within a few 10 million years or less, they could create all the planets, but they ran the codes anyway. They kept the running of the codes. This is a snapshot out at 850 million years. Watch it very carefully, because here's what happens. You see the outer planets are on the order of 20 astronomical units away. Okay, so now we're going to run it. Planetary interactions occur. These are called gravitational resonances, where Jupiter is fighting with the planets. Jupiter moves inward and it throws the outer planets outward. And the rocky material and the icy bits rain inward and hit the moon. And this happens at 3.8 billion years, right when we see these new basins being made. Okay? And now we can put the planets where they should be because of this interaction. So here's a summary. We create the planet's interior to about 20 astronomical units. The interaction occurs, the planets move out, and material rains inward. And then the large planets sweep up the remaining material, leaving two major pieces, the asteroid belt, which was a failed planet, never got together, and the Kuiper belt, well beyond the orbit of Pluto. This fits perfectly, and it comes from knowledge of the rocks from the moon. What about the future? What else do we want to do with the moon? Well, I want to tell you about one of the most startling and exciting discoveries that has occurred just in the last few years about the moon. And it starts by looking at the poles. So these two images are from the Lunar Reconnaissance Orbiter of the South Pole. The one on the the left, is the shadows. So as the moon moves around Earth, you get all the shadows, you get all the lit areas, and you see that even after 1 month, the moon's orbit, we don't find light in all locations. There are permanently shadowed craters, okay? And then the image on the right is indeed temperature. And what we see is those locations are really cold, And then we have another measurement that we made, and that is buried hydrogen. And this is typically in water form or hydroxyl form. So it's H2O or it's OH, okay? That inhibits neutrons from leaving the surface of the moon after it's being bombarded with cosmic rays. So it's a secondary reaction. We can make that measurement. And so these blue areas show us where water might exist on the moon. And it's in these permanently shadowed areas. So how did the water get into these permanently shadowed areas? Did that happen when it had an atmosphere and it was boiling off and it moved? Okay, or does it happen in natural water process that we don't know much about? Now, this is a startling discovery that we have water trapped in the permanently shadowed regions of the moon, because if we can go there and we can extract the water, we can then break it apart and we can create oxygen and hydrogen for rocket fuel, and we can breathe the oxygen. It's a game changer because it enables us to then not take everything that we may need to support a variety of human activity on the moon. So we have discovered in the last few years a water cycle on the moon. Now, this might be from material that's being emitted from the moon, and it looks for cold areas when it comes down. It might be from this early atmosphere. We don't know much about this water cycle, but we want to get into these craters and we want to look at it. Our current estimate is that there's anywhere from 100 to 200 million tons of water, and that may actually be a conservative estimate. So what are the things that we want to do? We want to go back to the moon and acquire material all over the place. We want to look at the mineralogy, but we want to date that material when we bring it back, because that will give us an accurate chronometer of everything that happened in the solar system by comparing the cratering rates at the moon with other objects in the solar system. We want to know more about this giant planet migration, okay? This is pretty startling when you think about how can you move huge planets like Jupiter, and it's through gravitational interactions. This now makes an enormous amount of sense, because when we look at exoplanets, we see large Jupiters on highly elliptical orbits or circular orbits really close to their suns, where there's no way they were created in those orbits. They had to have been moved there, okay? And so that has to be done through a gravitational fight between these large bodies. One gets thrown in and the other one gets thrown out, all right? And so those dynamics we're seeing reflected indeed in exoplanets. We want to be able to understand that water cycle more. We want to really see if our estimate is right. It may be conservative. There may be a lot more water there. We want to be able to look and see how the solar wind has impacted the regolith over time. Now that's important because we don't know a lot about the history of our sun. We know when the sun was created, it was nearly 30% dimmer than it is today, okay? And as the sun evolves, the sun will get hotter, okay? And so how active was the sun? During the time the sun was dimmer, we now know Venus, Earth, and Mars were all blue planets. How could that be when the sun was so dim? We need to understand that history of the solar wind, and we think that history is laying in the regolith on the moon. So we want to go back and we want better seismic measurements. We want to see the size of the core of the moon. We think it's small because most of that core material ended up inside the Earth. And so there's many things that we want to uncover, and this is the way to do it, by going back to the moon. And we have a space directive to do that. Space Directive 1, which was issued in December 2017 by the administration, says, you will return to the moon. Actually, that's not quite right. You'll go forward to the moon. Let's not go. And when you do, you will be able to learn to live and work on a lunar surface, on a planetary surface, and then go on to Mars. And we'll do this in unique ways by connecting with our commercial groups and by connecting with our international community. And so NASA's created a plan, and that plan has to be now accelerated because just a week or two ago we got another directive that states that this administration would like to see humans on the surface of the moon in the next 5 years. Well, this is still our plan. We're developing the orbital structure to be able to do that. One of the orbital elements is called the Lunar Gateway. This is a mini space station, if you will, that has a lunar habitat module, and then has high capability ion engines. It has sample ports where we can acquire sample. It has the ability for astronauts to live and work, and telerobot activity on the surface of the moon. And on the surface of the moon, we have a whole series of landers and rovers and, that we have planned to work with the commercial groups to be able to acquire those samples, make those measurements that we want to do over time. Now, the Gateway is a fabulous mission in the sense that it will orbit the moon in this highly elliptical orbit, and it will enable communication from anything on the far side of the moon. That'll just blow open that region. You know, for a planetary surface so close that we really haven't interrogated, it will change our knowledge of the moon-Earth system and will enable us to do an enormous amount of fantastic science. And that solar history is mostly on that far side once again. And so this is a spectacular step forward, and we already have international partners that we're connecting to. These international partners, Canada has signed up for the ARM, and ESA and JAXA are also creating plans to work with us on some of these habitat modules. Now, the long range, we also have to develop a variety of other technologies. The mobilities, the systems, the power systems, the ability to move over long periods with ion engines. The type of surface suits may have to change from the shuttle or Apollo-style suits that we heard about just in the previous wonderful lecture. And so we have a really bright future ahead of us as we move out in this particular direction. So the future of the moon, science and exploration, you bet. We talk mostly about the science, but indeed once humans begin that process of going there to living and working on a planetary surface, we'll have the opportunity to develop an understanding of how much water is there, whether we can use it as a fuel depot. We'll have an understanding of the platinum group metals that are on the back side of the moon. That far side of the moon, actually, we believe, has a significant number of impacts of unique platinum group metals. And so we want to get access to those, and we'll probably use those on the moon and maybe beyond the moon before we bring them back to Earth. So manufacturing and a whole series of other things that we want to do. So this is a pretty spectacular time. There's even some mining companies. Colorado School of Mines have come up with a really special way to be able to create a dome over these permanently shadowed regions, focus a solar light from the crater rim, shine that on the lunar crater surface, and that liberates that ice. It changes it from solid into vapor, and then acquires that material in a very easy approach. So many of these ideas are starting to come about as we begin to learn more about how to use the resources of the moon. So it's a wonderful time, and I'm glad you're here for the ride. Thank you very much. Thank you.
Hi, I'm Dave Eicher, editor of Astronomy, and I'm here in beautiful sunny California at Celestron, the world's leading manufacturer of telescopes. Today we're going to get the lowdown on a secret, a new hot product that's unlike anything you've ever seen. So let's go inside and check it out. So Corey, Celestron has a really new, exciting, unique telescope. Tell me about the RASA 36.
Yes, the RASA 36, it's a 14-inch RASA. We have had the 11-inch RASA out there for a while now, and we have been secretly developing a RASA 36, a 14-inch version of it. It's still at f2.2, so you will get you very good speed, but with increased aperture.
And this is a really wide field, high-tech camera, astro imaging camera. You could capture incredible wide field views of the Milky Way, big vistas of comets, but there's a really special application that this telescope is perfect for. Talk a little bit about that.
We've been getting feedback from different people. One of them is from a lot of users in the SSA community. SSA stands for Space Situation Awareness. What that means is space junk detecting. More and more satellites are out in orbit, and inevitably they will hit one another, and they become space junk. A lot of them will stay up there for 25 years, and depending on in what orbit they're in, you can be up there forever. What SSA community does is they track these junk so that we can notify the satellite operators so they can maneuver to avoid them. We identify the need, we find a solution. We want to make astronomy fun, and at the same time, we also want to keep everybody safe.
For over a decade, the FirstScope has been one of our customers' favorite products. It's easy to use, affordable, and provides really impressive views for a scope of its size. When the time came to update the FirstScope, I teamed up with renowned lunar imager Robert Reeves to create a telescope that would inspire the next generation of amateur astronomers to explore the moon.
Hello, my name is Robert Reeves. For the past 59 years, the moon has been my passion. Why? Well, the moon is the closest world to Earth. The moon is in our sky almost every night. The moon is close enough that we can see amazing detail on the surface with even modest telescopes.
The Robert Reeves Signature Series FirstScope is more than just a telescope. It's your guide to the moon. The telescope tube is a map of the moon's most notable features so you can learn the moon's geography. This telescope walks you through the basics and unlocks the entire hobby of astronomy, making it fun, easy, and accessible for everyone.
So I invite you to get out under the stars and enjoy a voyage to the moon.